Okay.
Oh, dang it, I don't have my calculator. Oh, mine's in my car. Oh, wow. I'm going to go. I need that. Yeah, I'm talking about exclusive.
Okay, so here's our first example here. Here's our first example here. Makes sense. Okay, x squared plus x plus 1 all over x squared plus 1. Okay, so again, we're kind of like following in the same steps as we had before with, natural log integrations things. So, and this is, after learning U-Substitution here. So, ideas here. What should we do? Let U equal what?
Back to the top.
Back to the top?
Yeah. Can we make that
All right, so let's just pause real quick. Hold on to that thought. Let U equal. So can we use a U substitution here, or is a U substitution going to be helpful?
I think yes.
Well, I mean, let's look here. So if I let U equal what though?
Well, we have to manipulate it first, do we not?
Oh
no, we can't factor that.
What do you need? What do you need, Emma? I do not have white out up here. No, it's up in my back of my desk. So, okay, let U equal what? So we can say x squared plus 1, right? But then we get 2x dx, which is not what we have up here. We have an x squared plus x plus 1 dx. So that does not help. So no. Okay.
Oh.
If we let U equal the numerator, that's not going to help either. So we need to rewrite this somehow.
Question.
Yep.
If we did du equals 2x dx divided by 2, could we not write u plus du on the numerator? That's x squared plus x plus 1.
Yeah, but then we have a u plus du, and this it always is like a times du there. So that's gonna be a problem. Yeah, it won't work right. Yeah, James, question or answer or idea?
Could you break it up? X squared plus x.
Okay, so break up the numerator to be x squared plus x over x squared plus 1, like this, dx, and then plus 1 over x squared plus 1 dx, like that. Okay. Ooh, yes, and actually, hang on a second now. What I'm realizing that we won't be able to do this with the way it's currently written.
Oh, man.
That's why. Okay, sorry. I thought I was being good about teaching guys this, then that, but I realized nope. Okay.
Please cross this out. Please remove all that crossed out.
Actually, hang on.
All right. You do it. You just do it.
So we can't integrate this yet. We don't know how to integrate 1 over x squared plus 1. You do, and you do, but yeah. James and Trinity do, but unfortunately that's not going to help work for us. So we're not going to go this way. Okay. We're going to long divide here. We're actually going to divide this.
I don't know how to do that, Mr. Woody.
Okay. So we're going to actually do the division here. So let me show you a little side work. Okay, guys, just listen, please. Just follow along. All right. Thank you. Comments are enough right now. Thank you. Okay. So we're going to do long division. Yes. All right. And so let's see what happens here. So if I write this, we're still not going to be able to integrate this, though. Why is this here?
Just cross it a lot.
All right, we're just going to roll with it here. All right. So anyway, 1, right? So how many times does x squared go into x squared? Once. So we're going to do 1 times x squared, so it's minus x squared. 1 times 1, all right, so that'll be minus 1 over here. Or plus 1, I should say, plus the quantity. Oh my gosh. This is...
Mr. Wood, I don't remember how to do this.
Yeah. I never knew how to do this.
You're making stuff up, Mr. Wood.
No, don't you bring the x down?
All right.
That,
Is that it?
That's it.
Wait, but don't you bring the x down?
I'm impressed. I don't even know where that come from. Not at all.
Okay. So there it is, rewritten after the long division. Okay, so let me re-explain the division here. So we're taking x squared plus x plus 1, and we're dividing by x squared plus 1, the quantity, right? Okay. You look at your lead term, just like you normally do long division. Right, everyone's like, I don't do long division, so I don't know how. So you look at your lead term here, it's x squared. You look at your lead term here, it's x squared. And you say, all right, I need a number here that's going to multiply by x squared to give me x squared. Well, that's 1, right? 1 times x squared gives me x squared. So so it's 1 times x squared right there. Okay? And we multiply the 1 times the 1 here, and it's 1 right there, plus 1. I put it underneath this because the numbers, that matches up. Those are like terms, they match up. Okay? So it's 1 times x squared, 1 times 1, 1. Just like if I take, 6 and divide it into 84, right? You guys remember doing this? Yes? How many times is 6 going to 8?
2.
1 times 6 is 6. We're left with a 2. We bring the 4 down. How many times does 6 go into 24? 4. 4 times 6 is 24. So it's, yay, no remainder. Okay, so it's 14 is your answer. Here works for polynomials as well. X squared plus x plus 1. How many times does x squared go into x squared? 1. So it's 1 times x squared, 1 times 1, 1. Again, I put it over there because they're like terms. And we subtract that quantity. X squared minus x squared, it cancels. X minus is x. 1 minus 1, 0. So it's just x you're left with. Now, x, okay, if you look here, what does x squared multiply by to get x? Well, we can't, right? That's our remainder. And so we're left with our remainders. We add x over, and then, we're still dividing by x squared plus 1. This x still needs to be divided by x squared plus 1. So that's why we leave it like that. Okay? That is the division. So there is what that simplifies to. All right? And so we integrate this. And we're going to break it up. Okay, question. Donovan, and then Ryan. Sorry? I mean, so all of these problems, like all the ones we're doing right now, we're going to be utilizing it, yes. Yes. So you'll see how I kind of got an idea for it. Ryan, yep.
all right, so to avoid the long division, couldn't we just do x squared plus x plus 1 times, in parentheses, x squared plus 1 to the negative 1, and just do that?
No, you can't multiply something that's like to the negative 1 if it's in parentheses.
So
Sure you can.
you want to bring this up into the numerator and say x squared plus 1 to the negative 1 like this times x squared plus x plus 1 like this? That's what you're saying?
Can't do that.
Yeah.
No.
And then how do you want to integrate that? Or how do you want it, then what? Is my question to you.
Well, distribute the negative 1 to x squared plus 1.
It doesn't work like that.
You can't do that. You can't distribute an exponent over addition. You can distribute an exponent. If this was x squared times 1, then absolutely it would be x to the negative 2 times 1 to the negative 1. You can't distribute over addition. So no. Emma. 1 dx, yes.
Really?
Yeah.
You did that?
Yeah.
Ryan.
Okay, so the integral of 1 is x. So I'm going to put a plus c there because we already integrated that piece. This piece, okay, now what can we do? To integrate this, what can we use? U-Substitution. Now we're going to let u equal what here, James? X squared plus 1, you got it. So then du is 2x dx. We don't have 2x dx, we just have x dx. So it's 1/2 du equals x dx. And so this becomes then 1/2 the integral of 1 over u du. And so we have x plus c plus 1/2 the natural log of the absolute value of x squared plus 1.
Hey.
Okay.
Nicely done.
Now, again, we've kind of answered our problem, but we could do a little more simplification here, potentially for like a multiple choice kind of answer. Maybe we would need to manipulate just a little bit more. For example, the absolute values. Are these absolute values necessary in this problem? No, because x squared plus 1 is always going to be positive anyway, so we can drop the absolute values. What about this 1/2 in front of the natural log?
Put it over 2.
Right, so we can put that in the kind of log there as
So is that
x squared plus 1 to the 1/2 plus c.
That's considered more simplified to put it in the log?
I don't know if it's more simplified, but again, just in case you need to be able to manipulate things around, I'm showing that to you. Okay? Let's try another one here. So again, the trick there was being able to do that long division, all right? Yeah.
I thought you said before we started this that it wasn't going to work.
The way that we were working here was not going to work, yeah. We don't know how to integrate that just yet. And I think James was going for that. I mean, you know how to integrate that, right, James? Right. So I think he was going for that because he saw it was something that he knew how to integrate. We're going to know how to integrate that after this. So that's why I think he was trying it that way. But we can't do that yet with what skills we have, and we don't need to. Okay? You'll see what it is. All right, next one, integral from 4 to 6. Now we'll just do a definite integral here. Okay, so obviously I'm not expecting you guys to, like, every time you come across a new problem to, like, just go ahead and long divide it. The first thing we should check to see is, do we need to long divide? Like, can I just go ahead and straight up use a U-substitution here? We can kind of see, though, that a U-substitution will not work, right? If I let U equal y minus 2, well, then my derivative is not going to give me that. And then if I let my U equal the numerator, well, I'll get something kind of like y minus 2, but it won't work still because this is in the denominator. I need 1 over y minus 2. Okay, so are we okay there with seeing that a U-substitution here will not work? We all see that? We can see that, yes? Okay, again, if I let U equal y minus 2, then the derivative of that's just going to be dy, but I have all this stuff up here to deal with. And if I let my U equal the numerator, well, it's going to be, what, 4y plus 7. I have y minus 2 here, again, still won't quite work. So we have to do something else, and again, we're going to do the division, okay? We're going to do the division here. So, let's go over here, I'll do some side work. I'll do it like right here underneath. So we have 2y squared, okay, plus 7y minus 3. And we're going to divide that by y minus 2. Okay. So let's see here. So Chanda, what do I multiply y by to match to 2y squared? Yeah, 2y, yeah, exactly right, yeah. So 2y times y gives me 2y squared. 2y times minus 2, yeah, minus 4y. I'm going to put that underneath the 7y because that's like terms, or that's a like term. The 7y, and then we subtract that quantity, okay? Remember, long division, this quantity here you just wrote down, we subtract that quantity. So 2y squared minus 2y squared, it cancels out. 7 minus negative 4y yields what, Chanda? Yeah, 11y. Bring down the minus 3. Okay, can I multiply y by something to get 11y? Yeah, 11. So plus 11. 11 times y is 11y. 11 times minus 2 is minus 22, and we're going to subtract that quantity. So the 11's cancel. Negative 3 minus negative 22 is positive 19. Okay? So plus then, that's my remainder, plus 19 over y minus 2. Okay? And so this becomes then the integral from 4 to 6 of 2y plus 11 plus 19 over y minus 2 dy. Okay, so now we're going to integrate here. And in fact, I'm going to kind of, let's see, how do I want to do this? Well, I'm going to break this up. The 2y plus 11 is easy enough to integrate, right? So let's just make this 4 to 6 of 2y plus 11 dy, and then we'll add to that the integral from 4 to 6. And in fact, I'm going to bring the 19 out front of 1 over y minus 2 dy. Okay, so you see how I broke that up? I kept the 2y and 11 together because they're going to be easy to integrate. So 19 over y minus 2, I made that into a separate integral here, okay, which I can do because addition, right? You can break up an integral over addition. And then, what do we have to do to integrate this one? What do we have to use?
Natural log.
Yeah, it's natural log, and we're going to have to use the U-Substitution. Granted, it's a very kind of elementary U-Substitution, but we still should just because it's the quantity y minus 2. Okay, so this first piece is easy to integrate. We get y squared plus 11y. I'm going to put the plus c in there. Okay. And then plus 19, and let's see, we're going to let u equal y minus 2. So du equals dy. And so then this is the integral of 1 over u du. Or du over u. Okay, and right, we know the integral of 1 over u is natural log of the absolute value of u. So it'll be 19 natural log of the absolute value of u, which is then 19 natural log of the absolute value of y minus 2 plus c. Okay. And evaluate that from 4 to 6. And so we get 6 squared plus 11 times 6. We can just do that math. Don't forget to put parentheses around your upper limit. Okay, so I have parentheses around my upper limit plugged in, so I plugged in 6 here. Yes, I have a 4, but that's because it was 6 minus 2, so it ends with the 4. And then minus the lower limit quantity, so 4 squared. And then 4 minus 2 is 2. Okay, like so. And then again, you're done there, right? If it's a free response question. But since we're here,
Why do you need
6, I don't know.
put the first
Set right here.
below that?
Here?
Yeah, I mean, like, is it just to show that quantity?
Yeah, I mean, I guess you don't need the parentheses there, but you definitely need the parentheses here.
Yeah.
You're right. It's kind of like, yeah, I think it's just more for organization's sake. You don't have to put these upper, the quantity, the parentheses on the upper limit, I guess, but the lower limit you definitely need parentheses around, so, because otherwise we'll forget to distribute. So let's see here, plus 19 natural log of 4. Oh, I can drop the absolute values, but oh well. Minus 16, minus 44, minus 19 natural log of 2. And let's see here, yeah. 36 plus 66, 102.
Yep.
Minus 16 is 84, no, 86. And then minus 44 is 42.
Yep.
Okay, now this is actually kind of crazy. And then again, I don't know if the test will, if like the AP test would be this mean. But you can actually combine these two together too. So natural log of 4 is 2 squared. I doubt it would be this crazy, but just in case, I'm going to show it to you here. 2 squared, that 2 exponent can come out front. And 2 times 19 is 38. And so 38 minus 19. And again, they're like terms. 38 natural log of 2 minus 19 natural log of 2. So we're left with 19 natural log of 2. Easy. So the calculus stopped right here. maybe here, and then algebra. So, yeah. Yeah, you could have stopped here if it was a free response question, but I also want to show you that you need to be able to simplify it too, potentially if it's a multiple choice, down to something like that. It is a lot. Yep.
Did you have to do all that like natural log work to simplify? Because 4 minus 2 is 2, or is that just a coincidence? Because they have the same. Couldn't you just keep the?
What you could do is factor out a 19 here, and then it would be 19 times the quantity, natural log 4 minus natural log 2, and you subtract 2 natural logs, you can then just divide to simplify. So that's another way to do it, yeah. But anyway, there's the final answer there, okay? So, the key to remember here, okay, just like your key, if a rational function, so you know what I mean by a rational function, right? It's a function that's got like a numerator and a denominator. If a rational function has a numerator of degree greater than or equal to the denominator, okay, so if a rational function has a numerator of degree greater than or equal to the denominator, divide, then integrate. Okay? So you might have to simplify it that way. Okay, so that's kind of a clue, okay? If you see that, in the wild, when you're doing some calculus, and you're like, wait a minute, I can't figure out what my u is, but my numerator is bigger than my denominator, or my numerator is the same degree as my denominator, then you need to do long division. Okay? All right, I got one more here for you to do, and then we're going to get into inverse trig. And this one is kind of, still in the same vein of things, but it's not what we just did. Anyway. A population of bacteria is changing at a rate of dp over dt 3000 over 1 plus 0.25t. Okay, so let's not be scared here by the fact that it says dp dt. Why do you think it says p there? What's that standing for? Population. And what's the t stand for? Time. So this is saying dp dt, which is not just the population. What is it really saying then?
Change of population over time.
The rate of change of the population over time. So this is like the derivative of the population function. Okay, so where t is time in days. So all this thing is the rate of change of the population over time and days. The initial population of bacteria is 1,000. Find the population of the bacteria after 3 days. Okay? So go ahead. We'll let you guys do that one.
This is calculator or not?
You shouldn't need a calculator for this. I'm going to say no calculator. You can use your calculator if you want to, I guess, but try to do it without a calculator, okay? Or at least, until you get to like the arithmetic.
For learning.
Try it without a calculator, though, because you should be able to integrate this by hand, for sure. on the total population of the bacteria after 3 days. Correct. Not, yep, the population of the bacteria after 3 days.
No, that's good. Yeah. You can type that into your calculator if you want to get a final answer. If you want to like evaluate the final answer to get like evaluate the final kind of math or to get like a decimal answer, that's fine. Yeah, and that's your what's this number here? That's U.
Yeah, sure.
No, T is how many days. No, that's exactly it. Right here. Yes, that's exactly it. Yep, so you're right. You got it. Pretty easy to check. Not sure. Gotcha. Okay, so when you're given the rate of change of a population, and you want to find like the net change. Again,
Good job, young boy.
just like you have a velocity, you want to find the net change position, you integrate the velocity. So we're going to integrate. We're going to integrate from what to what though, in a definite. After 3 days, right? So what would that interval be? From interval from what to what? We want to know what happens. N is 3. Correct. That'll give you the net change in population.
It's like,
That'll tell you how much bacteria grew over the first 3 days. But you're not only
It's not like
how many
1,000.
grew over the first 3 days. You're going to know the total population. So once you find that interval, then what else do you do?
Wait, the thoughtful way.
What else do we know about the bacteria's population?
I think you're right. Especially for the disease patients.
1,000 plus.
I'm so tired.
Shut up. Oh. 3,000. Trying to get one of the points of 5. Well, this should be 12,000. Not even 12,000.
I got 13,100.
Oh, I see that. Yes, we did. Yes, you did. Yep, you should do that, right? You added 1,000 at the end. So sorry, that was a mistake. I didn't know that. Yes, you're right. Yeah, don't add it. Yeah, okay.
Oh, wait.
Oh. Yeah, that's set up. Yep, generate that. What do you think you should do? How to enter the calculator? Well, for example, there's 3,000 numerator. You pull that 3,000 out, and get 1 over 1 plus 0.25t. Okay, so that looks good. Okay, these are your x limits of integration, not your u limits of integration. So you evaluated the back end for you, but you need to like adjust them.
Oh, okay, so plug these into...
Yeah. Okay. Exactly. What'd you get? Okay, so that's the net change, yes. Sorry? Well, I mean, I want the total population after 3 days. The change in the population after 3 days doesn't tell you how many bacteria grew over those 3 days. But then you need to know what will the total be. Well, if we started with a population of 1,000 bacteria,
This
it would be 1,000 plus.
Oh, should these then be the new limits?
Yeah. Okay.
So then
Just have to adjust your answer there. I think these can be flipped. So I think you integrate it from 0 to 3, right? So this becomes 1.5. The 0 becomes the 1. You got your
This never comes back.
So yeah, same deal.
Or it just throws them over there.
So this goes around somehow. James
Caleb, I think your jacket's in my car.
Clothes smell
Yeah.
so bad.
Well, no, that's, yeah. I gave that, and I was like, so, it depends, the question doesn't specify, so I would say, go with this, you say.
What do you have?
No, I asked CJ. I just didn't know.
Right, exactly, so, but I mean, again, it didn't say how to round, so I.
You guys
always
circle down,
assumed
grab
it's
it.
like-
Thanks. Anyone still need more time with this?
Finally, he asked them when he kept on.
All right, so there it is, folks.
Will they accept 0.389 of the bacteria?
So they didn't specify. So since I didn't specify. So I mean, I think yes, they would have to. I mean, you would have to accept that. They'll specify. They'll specify whether it's supposed to be rounding to the nearest, rounding to the nearest bacteria or not.
I always thought that they would you'd have to infer it several times. You'll never.
I don't know. Questions on this though?
We're getting to inversion.
We're gonna start it. Oh yeah, we got 10 minutes. We're gonna do it because we spent a lot of time, doing
So we just corrupted Connor.
papers and stuff.
He's talking too much.
Actually, that's a Hindu symbol for good luck. The Nazis appropriated that from the Hindus people. So.
What, this?
That doesn't make it any better.
No, the swastika.
It's still a Nazi.
That makes it like this.
No, yeah.
Good luck.
You go to like India and you look at in their temples and stuff like that, they have swastikas all over the place.
Oh,
It's
you're
like,
like,
oh my gosh, they're Nazis! But it's like, they're Indians, so no.
That is really fun. Super nasty.
All right. Anywho, yeah, they're secret allies in World War II. So okay. So no questions on this. We're all okay here. All right. So this one didn't really involve that division I just had showed you, but it is an example of something we need to be comfortable with doing. Right? We have a rate. Okay. We want to find the population of bacteria after 3 days. So we integrate that rate from 0 to 3. That gives us the net change, right? This is our net change of population. But we weren't interested in the change in the population. We wanted to find the population. So we had to take that change in the population and add to it the initial population of 1,000 to then yield 7,715 or 7,715.389 bacteria. Okay? So that's the idea there. Question?
So if this had been like water flowing into the tank instead, like there was nothing in the tank, it would have just been the original like change in.
Right, if the tank, if like this were like a rate of water flowing into a tank and the tank was initially empty, then you would just do the integral. Okay?
If it doesn't specify, would we assume that there was something in like, if there was ever a question on the AP exam, like.
If it doesn't specify, you assume it's empty then, it's just, yeah. But they'll specify, and sometimes you gotta be real careful where you look for it and stuff like that, you know, about where, how they do tell you what it is and stuff like that. You know, so anyway. Okay, let's get started at least into inverse trigonometric functions here, and we won't be able to finish it, so we'll finish up tomorrow. Okay. So we're going to do okay, so you guys remember doing the derivatives of these things, and you probably remember the pain, right, and the hatred for them. Well, now we're going to talk about their integrals. Okay. So remember, for example, that the derivative with respect to x of the arctangent, that was the most common one that I told you guys. You would see, 90% of them that you're going to see, if you see it on the AP test, 90% of them will be arctangent. And the derivative of arctangent is 1 over
1 plus x squared.
1 plus x squared or x squared plus 1. Either one. The other two have the square roots in them. Okay, the derivative with respect to x of the arcsecant of x, I think that's like the next most nope, it's arcsine is the next one. Oh well, whatever, I'll do arcsecant here anyway.
No, arc crossed out the E.
Life.
Now we have arc sick.
You can you can change it and do yours. I mean, you don't have to do the same order that I do mine. Okay, derivative of this is 1 over the absolute value of x squared root of x squared minus 1. This is like the most rare one you'll see. There's like a near 0% chance probably you'll see this on the AP test, but I still have to teach it to you because it's in the testing limits. So there it is.
So you're going to test it on?
I will let you know if it shows up on the test or not. How about that? And the last one is arcsine, which is the second most common one, really. So it goes like 1, 2, and then 3 in order of how typically you'll see them. And the derivative of arcsine of x is 1 over the square root of 1 minus x squared. It's similar to arcsecant. It doesn't have the absolute value of x in front, and the 1 and the x switch places. Okay, so those are the derivatives. The integrals are just these things basically in reverse. So, for example, reverse, exactly right. So the integral of du over a squared plus u squared. So notice we're changing up just a little bit here. We're not putting 1 plus x squared in here. We're gonna make it more generic than that. So instead of saying 1 plus x squared, I'm doing a squared. So there's a number squared plus a function squared here. And that equals 1 over a times the arctangent of u over a plus c. So the integral is a little more complicated than the derivative is. That's because we have things like U-Substitution and stuff like that we'll still be able to use here. Okay, so that's arctangent. Let's see here. Arcsine. Okay, again, it's square root of a squared minus u squared, so like the 1 minus x squared, so there's your number squared minus your u squared, and that's going to equal no 1 over a here, just arcsine of u over a plus c. And then the integral with respect to u of u times the square root of u squared minus a squared. Okay, that one's going to be then the arcsecant. It's 1 over a arcsecant. Yeah. I mean, you'll see some for homework and stuff like that, but I don't know if I give you, I'll let you guys know if I give you one on the test or not. You should know it. Okay, so those are the integrals right there. And it's like, oh crap, right? Those are kind of tricky looking.
So these will be on the test on Wednesday?
Friday, and
It says Wednesday.
Geometry, buddy.
it does say Wednesday for geometry.
I didn't have my coffee this morning.
Mm.
I'm actually like sitting here like sleeping. I
Yep.
won't even remember this class. I won't even.
All right, so let's do some examples here, and then.
Fine, we're gonna take advantage of that.
All right, so we're going to integrate. Let's see these in action.
I don't think we've ever taken this all the way up to the end of class before.
We haven't been taking notes all class long though either, so.
Yeah.
I feel like this is our normal amount of time for notes, and it's just, yep, and it just kind of bumped into the end of class because of how long it took me to collect everything. Okay. We're probably just going to end up doing one because of time. Okay, so, looking at this, does it look like we're going to use arctangent? Why not? What's kind of cluing us in that's not arctangent? It has a square root, and what else does it have? It has subtraction, right? Arctangent is addition. Okay? Let's go to arcsine. Could it be arcsine?
Yeah.
Okay? A squared minus u squared. So it means it should be a number squared minus some, like a function kind of variable thing squared. And in fact, yes, right? So this is, I'm going to rewrite this just for our benefit here, as dx over the square root of 2 squared minus x squared, like this. Okay, it's going to be helpful to rewrite it this way. It makes it more obvious. Okay, because you can see, to integrate this, we need to know what is our u and what is our a. So what is u in this case?
I mean, x.
Yeah, I mean, let's look here. Let's be careful. Right? It's not as obvious maybe as we think, right? There's a squared minus u squared. So what's our u? It's x, right? It's the x here. It's the subtracted quantity, so it's minus u. So we're going to let u equal x. I know it seems kind of silly, but I mean, we just want to make sure it fits the format we want there. And so what's du then? Just dx, right? Which is what we have, dx. Again, we're not letting u equal x squared. We're just letting u equal x, because we need u squared here. So we're going to just let u equal x. And so then this becomes then the integral of du over the square root of 2 squared minus u squared, which is exactly what we got. We matched up there now. And so now we can integrate that. And so it's going to be the arcsine of what over what? Yeah, u over 2, and then we'll plug it back in, yeah. Plus c. So it's arcsine of then x over 2 plus c, and there's our final answer right there. Okay? So that's the idea. All right.